everyone, welcome back. The learning goal for this video is to describe the changes of state between solids, liquids, and gases, and calculate the energy involved. As we've discussed before, matter undergoes a change of state when it's converted from one state to another state. So once again, from solid, liquid to gas. And like I said, in this video, you'll be able to calculate the energy involved in those transitions. So let's first talk about melting and freezing. A substance is melting while it changes from a solid to a liquid at its melting point, and we'll abbreviate melting point as MP. A substance is freezing while it changes from a liquid to a solid at its freezing point, which we will abbreviate FP. For example, water has a freezing and melting point of 0 degrees Celsius. So if we imagine we have ice, and that's a solid state of matter, when it absorbs heat energy from the surroundings, whether you put your ice on a table and absorbs heat energy from the table as well as the surrounding air, it begins to melt. And that happens at 0 degrees Celsius to form a liquid. The reverse can happen. You can have liquid water, but you have to remove heat energy. So remember, the negative sign means that heat energy is taken away, it's removed. And if we put that liquid water, let's say for example, in a freezer where it's really cold, the water will start freezing into solid ice at 0 degrees Celsius. Melting and freezing are reversible processes. So they can happen at the same temperature. And there is a constant associated with the amount of energy it requires to melt or freeze a substance, and that's called heat of fusion. The heat of fusion is the amount of heat released when 1 gram of liquid freezes at its freezing point. And remember, heat is released when that process happens because we're freezing. Heat of fusion is also the amount of energy needed to melt 1 gram of solid at its melting point. So that heat energy is absorbed when we're melting. For a given amount of substance, heat released during freezing is equal to the heat needed that's absorbed for melting. And the abbreviation for heat of fusion is delta H, and then FUS as the subscript. So heat of fusion, that's a symbol that you will find. And the heat of fusion for water, to melt the water, requires 80 calories per gram, or 334 joules per gram. So you'll be able to find either constant with those two different units. And these numbers, these constant values will be provided for you either in a table or within the context of the problem. And usually when you find it in a table, you will see enthalpy of fusion for water, because it's different for every substance, is equal to 80 calories per gram. And it's only going to give you a positive value. Now that's okay for melting, because to melt ice, we need to add the heat energy. And so this would be called an endothermic process, because heat energy is absorbed but to freeze water, we need to release that energy. So it's on the what we call the product side of the arrow on the right side. Notice how it's on the left side of this one. That's an endothermic process. But for this process, heat energy is released, so that is exothermic. So exothermic heat energy is released. And we will discuss more of that later, but for right now, if you see heat energy on the left side of the arrow, meaning that it has to be absorbed, then it's an endothermic process. If you see it on the right side of the arrow, then that means the heat energy is released. So that's an exothermic process. Now we're going to use the enthalpy of fusion or the heat of fusion to do some calculations. Once again, always state the given and needed quantities, write a plan to convert the given quantity to the needed quantity. You'll write the heat conversion factor and any metric factor needed, and then we will set up the problem and calculate the needed quantity. So pause the video, try to see if you can do the study check on your own, and then come back and check your work with me. All right, we want to calculate how many joules are needed to melt 32 grams of ice at 0 degrees Celsius. So once again, we always write down our given and our need. So it looks like we have mass is equal to 32 grams. And it's important to write the identity of the substance because every substance has a different heat of fusion. And so remember, this is water as a solid. It's saying that we are melting. So that's also another piece of important information. We are melting. So that means we will need to look up the enthalpy of fusion for water. And this number here, 0 degrees Celsius, is the freezing point. So I'm put temperature and then FP for freezing point, or actually melting point, right? Because we're talking about melting here. So let's identify that as the melting point for water is equal to 0 degrees Celsius. Now that is a bit of extra information we will see later on. It's telling us how this experiment was done. So it is an important piece of information for the experiment, but you'll notice later on that we're not going to actually plug it into the formula. It's just telling us that this was done at the melting point for water. All right, so then it looks like it's asking we need to find joules. So we need to find heat energy in joules. And because we're melting, I'm going to look up the enthalpy of fusion for water. So we're going to use it as a conversion factor to solve for Q. So let's go ahead and look at the enthalpy of fusion for water in joules is 334 joules in order to melt 1 gram of water. It requires that much energy to melt 1 gram of water. All right. So when we solve this problem, Q is equal to the mass of the substance times the enthalpy of the fusion of the substance, or the heat of fusion. You've been hearing me interchangeably use the words heat energy and enthalpy. And in the context of chemistry, because we work at constant pressure with a lot of our reactions, they're the same thing. So heat energy and enthalpy end up being the same thing because we're working under constant pressure. So the heat energy is equal to the mass of the substance times the heat of fusion of that substance. And we can see that because the units are going to cancel out. So we have 32 grams, and then we're multiplying by 334 joules for 1 gram of water. So it requires that much heat energy to melt 1 gram of water at 0 degrees Celsius. But we have 32 grams of water. And so we are going to take 32 times 334, and we get 10,688 joules. Because this is multiplication, we will report to the least number of sig figs, so that's 3 sig figs. And so then the final answer is 107.00. We need those zeros at the end as placeholders to indicate that it's 10,700 joules and not just 107 joules. Now I imagine this number is quite big, so even though I didn't ask it here, a lot of times we will report these larger values in kilojoules. And so you may simply need to convert that there are 1,000 joules in 1 kilojoule. And so this is 107 kilojoules. Once again, the question asked for it in joules, so you could give that answer, but it's good practice to convert it into kilojoules because oftentimes we do work with heat energy in kilojoules or kilocalories. So if I have 32 grams of ice, it requires 107 kilojoules to melt the ice completely. If you did this question again, and you asked how many joules of energy are needed to be released in order to freeze 32 grams of liquid water into ice, you would end up with the same number. Because remember, freezing and melting are reversible processes. All that changes between freezing and melting is how the heat energy is transferred. For melting, it's an endothermic process, so heat energy is absorbed, which indicates that positive sign there. For freezing, heat energy needs to be released in order to cool it down, and so that's why it has a negative sign there, but they're reversible. All the difference is the direction of the heat energy. Let's talk about evaporation, boiling, and condensation. Now, water evaporates when molecules on the surface gain enough sufficient energy to form a gas, so from liquid to gas. The reversible process for evaporation is condensation, and that's when the gas molecules lose energy and form a liquid. During evaporation, molecules of the liquid are converted to gas at the surface of the liquid. So in this case here, we are boiling water in a beaker, and or actually another substance looks like we're boiling because it's at 50 degrees Celsius and water boils at 100 degrees Celsius. So we have a different substance here, or maybe it's just starting a little bit of those water molecules, even at 50 degrees, may start to evaporate. So there you go. You can see the surface. If we go to actually boiling here, that was the start of it. If we're actually boiling, now we've reached 100 degrees Celsius, the boiling point of water, so that was water. And you can see a lot more bubbles coming up. Those are those gas molecules trying to escape. So when water is boiling, all the water molecules acquire enough energy to form a gas. Another way to say this is that it's vaporizing. Bubbles of water vapor appear throughout the liquid. During boiling, once again, molecules of the liquid are converted to gas throughout the liquid as well as at the surface. So that's a vigorous boil right there. And then finally, another method of changing between states of matter is between sublimation and deposition. This is a little less common. When sublimation occurs, the particles on the surface of a solid change directly to a vapor. So we go from a solid to a gas. The reversible process is called deposition. When heat energy is lost, you go from a gas straight to a solid. Once again, there's no change in temperature when we go between states of matter. So for example, dry ice, which is solid carbon dioxide, sublimes at negative 78 degrees Celsius. And so you can see here, if you've ever seen dry ice, it almost creates like this fog effect, right? And that just means those solid CO2 molecules are going straight from solid to gaseous CO2. Now, sublimation is a very useful technique to help prepare freeze-dried foods for long-term storage. Some of my favorite freeze-dried foods are like freeze-dried strawberries or blueberries. Water vapor will change to solid on contact with a cold surface, and those freeze-dried foods have a long shelf life because they contain no water. Now, coming back to vaporization condensation, we will mainly be working with melting and freezing and vaporization condensation in terms of calculations and quantifying how much heat energy is released or absorbed for these processes. Sublimation and deposition is not as common. Typically, a few substances sublime or undergo deposition. So once again, focusing mainly on melting, freezing, vaporization, and condensation. So when we're discussing vaporization, condensation, these are also reversible processes. It's the amount of heat absorbed to change 1 gram of liquid to gas at boiling point. That's vaporization, an endothermic process. Condensation is when we go from a gas to a liquid, and that's the amount of heat energy needed to be released when 1 gram of gas changes to liquid at the boiling point. And so this would be an exothermic process because heat energy has to be released from our system. The heat of vaporization for water, remember it's at the boiling point. And so therefore, 100 degrees Celsius for water. It changes for different substances, but we're focusing on water right now. It's the heat absorbed when 1 gram of water changes to steam, okay, from liquid to steam. So you can see liquid to steam, which is a gas. It's an endothermic process, so the heat of vaporization is on the left side of the arrow. So that makes it endothermic. And remember, there's 2 different units, joules or calories, depending on what's being asked in the question. And the heat of condensation for water is the heat released when 1 gram of steam changes to water. So heat energy has to be released. So it's on the right side of the arrow, which makes it an exothermic process. And the value is 540 calories per gram or 2,260 joules per gram. All right. Go ahead and pause this video. Try this study check on your own and then come back and check your work with me. All right, so how many kilojoules are released when 50 grams of steam from a volcano condenses at 100 degrees Celsius? So let's go ahead and write our given. So we have mass of steam, which is water. So I'm going to always identify what I'm working with. So mass of water as a gas is 50 grams. And it says it's condensing. So that means, I'm going to write that as well, because that's a clue, that water is going from a gas to a liquid. And it says that how many kilojoules are released. So that's true. I need to figure out how much energy is released. So that Q, or that number, is going to be on the right side of the arrow. And it says condenses at 100 degrees Celsius, but I know that's simply just the boiling point of water is 100 degrees Celsius. It's not going to be plugged into the formula. It's just part of the experimental conditions to do this measurement. We need to figure out kilojoules of energy. So that's Q in kilojoules. We're working with water. It's condensation. So that means I need to look up the heat of vaporization. And that will be, and it's in kilojoules. So I need to do the 2,260 joules per gram of water. So in order to condense 1 gram of water, it requires a lot of energy, 2,260 joules. All right, now that we have all of our data here, let's go ahead and start to solve our problem. So Q, heat energy associated with a state of matter change, in this case, from a gas to a liquid, is equal to mass times the enthalpy or the heat of vaporization here, because we're dealing with condensation, which is just the reversible process to vaporization. And so this is equal to 50 grams of water as steam. And we want to condense that water. It's going to require 2,260 joules per gram. And when I plug that into my calculator, I take 50 times 2,260, and it's already 113,000. It's already in 3 sig figs, which is great. Few sig figs. Now the question asked for in kilojoules because it is a rather large number. So what are we going to do here? That's correct. 1,000 joules in 1 kilojoule. We're going to do that conversion. You can see, like, when we do any of the dimensional analysis, it's all about unit cancellation. So this final answer, if we divide by 1,000, is 113 kilojoules of energy to 3 sig figs. And that's how much energy is released, because condensation is an exothermic process. All right, so we've been discussing different changes between states of matter. Now let's apply that knowledge to what's called a heating and a cooling curve. So let's look at a heating curve. The diagonal lines indicate changes in temperature for a physical state, and the horizontal lines, the plateaus, indicate the changes of state. So up until this point in this video, we've been focusing only on the plateaus, when we've been changing the state of matter from a liquid to a gas, and then from a solid to a liquid. That's all we focused on. And then the diagonal lines indicate changes in just temperature for the same physical state. So when we look at a heating curve, let's kind of zoom in here. Looks like we're looking at the heating curve for water, because the first thing you want to look, the first plateau on the heating curve will give you your freezing melting point. So I'm going to go ahead and let's highlight that. So this here will indicate where it intersects the temperature, which is on the y-axis. That number will be your freezing point or melting point. So freezing point or your melting point, because remember, those are reversible processes, going from a solid to a liquid or from a liquid to a solid right here. And then also it's important that you can identify, like, before you hit the freezing or melting point, the state of matter is a solid. After the freezing melting point, it's a liquid. And then when you hit your next plateau, this will tell you your boiling point here, where it intersects the temperature on the y-axis. So in this case, once again, this is 100 degrees, same as the condensation point. We tend to refer to it usually as the boiling point, but understanding that both vaporization and condensation are reversible processes that occur at this plateau. And that is from a liquid to a gas or a gas to a liquid. Another observation you can make from heating curves is that they're all going up, so it's more of a positive slope. And then when we look at cooling curves, it'll be more of a negative slope. So go ahead, pause the video, answer the following questions on the study check, and then come back and check your work with me. All right, a plateau, a horizontal line on a heating curve represents what? There's two answers for this, so trick question there. But it is a change of state, so that's probably what most of you chose, but also it's a constant temperature. So remember when we looked at, for example, melting, on the heating curve, it's melting at 0 degrees Celsius. So not only are we going from a solid to a liquid at this plateau, but it's at the same temperature. And that, just as a reminder, was why we saw, for example, temperatures in the word problems, because they were part of the experimental conditions to do this whole problem. We didn't plug 100 degrees Celsius in there. In this case here, that was just telling you the experiment was done at the boiling point of water. A sloped line on the heating curve represents what? Good, it represents the last one, right? A temperature change here. So the other two were for the plateau, the constant temperature change of state, but the sloped line was a temperature change, and the state of matter is constant in that slope. All right, go ahead, pause the video, try to answer these questions on your own, and then come back and check your work with me. All right, now this says to use the cooling curve for water, which you can find in the next few slides. So hopefully you found that in the next few slides. We'll look at that together to answer the following questions. And that's what I would do for an assessment. I would have to provide the heating or the cooling curve for you to read and to gather data from. So for example, water condenses at a temperature of what? So let's go and let's find this here. And so now you can see on the next slide here, we have the cooling curve for water. And so in that case here, it condenses. Let's go ahead and just label this. This is a gas, and this is liquid water, and ice is a solid. And so condensation is when we go from a gas to a liquid. And it happens at the plateau at a constant temperature. So for water, it is 100 degrees Celsius. Good. So C for that one. At a temperature of 0 degrees Celsius, liquid water does what? So at a temperature of 0 degrees Celsius, what does liquid water do? Because it's a cooling curve, it is freezing. For the heating curve, it was doing what? It was melting. Good. So this is going to be A, freezes for this question here. At 40 degrees Celsius, water is a, so the way we do that is we go on the y-axis, that's temperature, 40 degrees Celsius, and then we walk across until we intersect the cooling curve, and water at this temperature is a liquid. When water freezes, heat is what? Is it added, absorbed, or is it removed or released? When water freezes, when it goes from a liquid to a solid, heat energy has to be removed. So for a cooling curve, heat is removed. For a heating curve, heat is added, or another word for that is absorbed. So they're the opposite of each other. So the answer for question 4 was A. Once again, as you can see here, this is the cooling curve for water. I could provide the heating or the cooling curve for other substances as well besides water, But those types of questions I just showed you in that study check are examples of types of questions I could ask you on an assessment to determine if you're able to read a heating and cooling curve confidently. All right, so go ahead, try to pause the video, try this problem on your own first, based on what we just covered together, and then come back and see how far you got. Check your work with me. So let's go ahead and go do this problem here. So calculate the total heat in joules needed to convert 15 grams of liquid ethanol at 25 degrees Celsius to gas at its boiling point of 78 degrees Celsius. Ethanol has a specific heat of 2.46 joules per gram degree Celsius and heat of vaporization of 841 joules per gram. So these are combining the different types of heat calculations we have learned in this video and in previous videos when we discuss specific heats, okay? So whenever we have combined heat calculations, I always find it nice to kind of set up, draw like what's taking place. So we'll write our given our need, but I also will maybe do a drawing for this heating curve here. All right, so let's go ahead and we are given that the total, needed to convert mass of ethanol. I'm going to abbreviate ethanol as ETOH, is 15 grams, and it's liquid ethanol. So liquid ethanol, that's what we're starting with at 25 degrees Celsius, which is room temperature. And what we're doing is we're heating it up to a gas. So eventually we're taking that and we're going to convert it into a gas at its boiling point of 78 degrees Celsius. So we're changing the temperature and we're also going from a liquid to a gas. And then we are given ethanol's specific heat. So the specific heat of ethanol is equal to 2.46 joules per gram degree Celsius. And a heat of vaporization is equal to 841 joules per gram. So we're given some constants, some data. But whenever I'm seeing like combined heat calculations, I like to draw the heating or cooling curve. In this case, it's a heating curve because we're going from a liquid to a gas. So temperature is on the y-axis and heat is added because it is a heating curve. And it looks like we are at 25 degrees Celsius, and that's when ethanol is a liquid. And then we're heating it up to the boiling point. So I'm going to do 78 degrees Celsius here. That's the boiling point. So before ethanol turns into a gas, we have to heat it up. So we're going to start here. It's going to heat up. We have a slope there in that line. So this is ethanol as a liquid, but with a change of temperature. But once we hit the boiling point, then we hit the plateau. And that is ethanol going from a liquid to a gas, and that's called vaporization. Therefore, anytime you're working with a heating curve or a cooling curve, you're going to do different calculations if you're going to combine them. We want to find the total amount of energy to do both of these, but to calculate the heat energy to heat up the ethanol, that's a different calculation versus the heat energy required to boil it to a gas. Okay, so there's two different calculations, and what we need to find is the total heat energy. That's our goal here. So we'll have to add them both up. And so what I like to do is say, okay, This part here in pink will be Q1. That's the first step, and that's a separate formula. And then this one in green is Q2. So it's the second heat energy we have to calculate, and then Q total will be equal. So Q total is equal to Q1 plus Q2. Now in this video, we learned how to calculate Q2. This is using the enthalpy of fusion or vaporization. So I know Q2 is going to be the mass times the enthalpy of vaporization when we do that one. Q1 though, we're not changing the state of matter. We're staying as a liquid. And we learned this in the specific heat video, although I had shown a calculation in the specific heat video to calculate specific heat. In this case, in this video, we will use the formula mass times the change in temperature times specific heat to find Q1. And so the way I always tell students, how do you know which formula to use? Well, if you're doing a plateau, which is meaning you're changing the state of matter, then you will do mass times delta H. If you are changing temperature, but keeping the state of matter the same, then you will use the formula from the specific heat video, which is mass times change in temperature. That's the clue. We are changing temperature times specific heat of that substance. So there's always two different formulas to calculate heat energy. You need to know what's taken place in order to choose the correct formula. So let's go ahead and do Q1. So Q1 is equal to mass of 15 grams times the change in temperature. Change in temperature, I'm going to do this up above here so I don't run out of space, is equal to final temperature minus initial. The final temperature is 78 degrees Celsius minus the initial temperature, which is 0 degrees Celsius. So 78 minus 25 is equal to 53 degrees Celsius. So I'm going to plug in the change in temperature here, 53 degrees Celsius, and then times the specific heat, which was given to us, 2.46 joules per gram degree Celsius. Remember, specific heat is a unique value for that substance, so we need to be given that for ethanol. In this formula, the grams cancels out, the Celsius cancels out. So when we plug this number into our calculator, these values, we will get Q1. So 15 times 53 times 2.46, and I got 1,955.7 joules. I like to keep all the numbers until the end, and then we can round at the end. And now let's do Q2. So that one was Q1. I'm going to go ahead and highlight that number. We'll need it in a little bit. Q2 is going to be equal to the mass of 15 grams times the enthalpy of vaporization, because now we're just converting all that ethanol from a liquid to gas at 78 degrees Celsius. So this will be that times 841 joules per gram. And I always like to check that my units cancel out, even if I'm plugging it into a formula. And so 15 times 841 is equal to 12,615 joules. Now I got to combine all those together. So I'm going to, we'll first highlight it so we know that's Q2. And then we need Q total. So Q total is equal to Q1 plus Q2. And this will be, let's see here, we have plus 12615, and I get 14,570 joules. Now, when you're dealing with calculations that involve mixed operations, so multiplication in this case, and then addition, Remember, multiplication has different rules than addition. I tend to be more lenient on significant figures if the calculations are not straightforward. Like what I mean by straightforward is that I would expect you to know how to do sig figs for the final answer for this. So, because it's 3 sig figs here, 2 sig figs here. So 2 sig figs, right? Because it's all multiplication. But because this whole problem involves multiplication and addition, then that can make the significant figures confusing. So always play it safe and do 3 sig figs. That's usually, universal for general chemistry. Sig figs typically is the case for a lot of your final answers. And so in that case, it'd be 14600 joules. So 14,600 joules as your final answer here for the energy total. So what that means is that if I started with 15 grams of ethanol, it requires that much energy first to heat it up to its boiling point and then to convert it all to a gas. All right, go ahead, pause the video, try to do the study check on your own, and then come back and check your work with me. All right, when a volcano erupts, 175 grams of steam at 100 degrees Celsius is released. How many kilojoules are lost when the steam condenses and then freezes at 0 degrees Celsius? So it sounds like we're doing a bit of a cooling curve here. All right, so let's go ahead and write down our given. I'm going to write it up here just to give me more space. So we are given the mass of steam, which is water as a gas. I'm going to identify that. 175 grams. When I see 100 degrees Celsius, I immediately think that's the boiling point or condensation point for water. I'm going to write that down, but I may not necessarily need that number. It might just be giving me experimental conditions. So knowing when you need to plug something in versus when you don't is important, but we'll keep it there. And this is how many kilojoules of heat energy are lost when the steam condenses and then freezes. So it sounds like I also need that freezing point there, which is 0 degrees Celsius. And I need the total amount of energy in kilojoules. All right, once again, this sounds like a cooling curve because initially it's really hot. And so let's go ahead and draw our cooling curve so we can see how many different types of calculations we might need to do. Temperature is on the y-axis. And because this is a cooling curve, heat is removed. And it looks like we are at 100 degrees Celsius to start with. And then we are going to want to freeze at 0 degrees Celsius and calculate the total amount of energy. So first it's steam, but we want to convert that water into a liquid. And then the liquid's going to cool. And then once it cools, then it's going to freeze. Okay, so because we have 2 different plateaus, so we're going to have a calculation for the first plateau. That will be Q1. That's for the condensation part. We will then have a different calculation, because it's a different formula for the second portion here. That will be Q2. And then we will have a third calculation, because once again, we're going back to a different formula here. And that will be Q3. And so let's go ahead and start. When we do total, we'll have to add them all up. But Q1 is a plateau. It's a state of matter change. So what formula do we use? Mass times the heat of vaporization, or mass times delta T times specific heat? Hopefully you said the first one, mass times the enthalpy of vaporization, because there's no change in temperature at that 100 degrees. We first got to convert all that water from a gas to a liquid at this point, and that's a separate calculation. So let's go ahead and do that. Is equal to 175 grams times the enthalpy of vaporization. So I'm going to have to look that value up. Once again, you may be provided a table or the numbers might be provided within the context of the problem. So heat of vaporization we worked with before earlier. So that is 2,260 for water joules per gram. And so that is 175 times 2260. And so we get quite a large number here. 395,500 joules. So I'm going to go ahead and highlight that in yellow because that's Q1. I'll need that number later. Q2, a temperature is changing. So we're going to do mass times delta T times specific heat. And delta T is the final temperature minus the initial temperature. And so in that case here, so delta T is equal to TF minus T initial. So that's 0 degrees Celsius minus 100. And you might be like, what? That is negative 100 degrees Celsius. But go ahead. The negative just means heat energy is removed. So it's okay to make this a positive value because that's how we're going to work with heat energies in this class. Now, for some of you who may take like a general chemistry course for science majors, we tend to keep the sign as negative, and we go into more detail about why that's the case. But for you all, I'm okay for you changing it, to a positive difference between final and initial when you're plugging it in. So in this case, 175 grams times, and I want to make it a positive value. So absolute value, 100 degrees Celsius times specific heat of water, 4.184 joules per gram degrees Celsius. And so when I plug that into my calculator, I get 175 times 100 times 4.184, and I get 73,220 joules of energy needed to cool all that liquid water towards the freezing point. Q3, now we're taking all that liquid water and converting it into solid. We're freezing it. So we need the mass times the enthalpy of fusion, because that's the freezing, melting heat of fusion. So that's 175. We would have to look up the heat of fusion for water, which in this case is 334 joules per gram of water. And you would get 58,450 joules of energy required to convert all that liquid water and freeze it into solid at the freezing point of 0 degrees Celsius. And then finally, we want to add it all up. So the amount of heat energy needed to be released is equal to Q1 plus Q2 plus Q3, which is 395,000 plus 73,220 plus 58,450 joules. And your final answer would be 527,170 joules. Let me double check. Yep, that looks good. So then remember with these types of problems, because there's a mixture of multiplication and addition, and those have different rules for significant figures, let's just round to 3 sig figs. So this would be 500,000, 527,000. And we would need to include those trailing zeros to indicate the order of magnitude. I'm just rounding to 3 sig figs here, but I can't drop those zeros because that would change the order of magnitude. And this question actually did ask us in kilojoules, so we would need to can do that conversion. So 1,000 joules and 1 kilojoule. So basically you're dividing by 1,000, you get 527 kilojoules as your final answer. All right, so this will wrap up this unit on matter and energy, and below is a concept map, but I encourage you to create your own concept maps, kind of organize everything we've learned, whether it's definitions or calculations, organize it in a way that makes sense to you. But let's just kind of review over this concept map here. So in this unit, we've learned the difference between matter and energy and their definitions. We studied extensively the different states of matter, solid, liquid, and gas, and understand their definitions. We were able to identify the difference between pure substances and mixtures. And within pure substances, what's an element versus a compound. For mixtures, we are able to identify what's a homogeneous versus a heterogeneous mixture. And in addition to understanding the changes of states of matter, we understand that heat energy is lost or gained during the reversible processes of melting or freezing or boiling or condensation. And in order to quantify the amount of heat energy either gained or lost, we needed to look up constants such as heat of fusion or heat of vaporization. And we can also draw heating or cooling curves to represent the changes in states of matter and also to help us do our calculations if we're calculating the total energy gained or lost for a process, like we just did in the last two examples. When we studied energy, we understand that energy can affect particle motion. Specifically, we're focusing on heat energy in this course, and we can measure heat energy as calories or joules using temperature change, specific heat of a substance, and the amount of substances we are studying. All right, thank you for watching. And as always, email me with any questions.